So here we go. So welcome to Intro to Deep Learning. We've already had 2 lectures, so a couple of things are probably already obvious. But my name is Mia, and David is doing this recitation with me. So we all know this. There are some tasks that are easy for us to do, like differentiating between a cat and a fox and a dog. But that might be harder for a machine to figure out. But machines can do a lot of heavy calculations that might be overwhelming or too difficult for humans to do. So here we see a drawing of a neuron. Our biological brains are made of connected neurons, and these are the inspiration for artificial neural networks. We can think of this neuron as having a threshold function that controls when to fire an output. So for example, if a signal isn't strong enough, the neuron can determine that there's no reason to fire. But as soon as the signal passes a certain threshold, the neuron produces an output signal. So in this class, when we refer to a perceptron, it's kind of a model of the neuron. Activation functions, we'll get to that in a bit. They include the threshold functions like this one with the light bulb, which could be like a 0-1 step function. Okay, so what are perceptrons? They are single layer neural networks like the one shown here with a 0-1 step threshold function. There are 4 parts. The inputs, which are passed in at the start of a forward pass. There are the weights, which are refined as a neural network learns. We'll get to that in a bit. It has the weighted sum, which is just the summation of the inputs multiplied by the weights. And then the activation function. So here I'm showing it as a threshold image from before, but really it's an activation function. And there are many different activation functions you can use. Here are the ones that you'll see most often in class, at least in this class. Perceptrons are binary classifiers. So here we're only seeing 2 options. The light bulb is on or off, and that's because that's all that a single perceptron can differentiate. Here's what it might look like if you wanted to use the perceptron to separate dogs from cats. But what if we have a fox, right? There's now 3 different animals. What we'll need is instead a multi-layer perceptron to include the fox. So just by adding a second linear classifier, we can demonstrate how adding another perceptron can help to differentiate between the fox and the other animals. As a multi-layer perceptron would. Okay, so here's an example of a fully connected multi-layer perceptron. It's fully connected because every node in a layer is connected to every node in the layer before and after it, aside from the inputs and output layers. So the yellow lines here are the hidden layers. We're going left to right with the input layer in red and the output layer in blue. And okay, the forward signal. We have the same colors here as before with the perceptron, with the inputs in red, the weights in purple, weighted sum in neon green, and the activation function in orange. So starting with the information about what a fox is as the input, we pass it forward through the first hidden layer to generate an output that will be used as the input for the next hidden layer. So again, we pass the new input from the hidden layer to get a second hidden output, which becomes the new input for the third hidden layer. And so on until you reach the final layer, which is just the output itself. Oftentimes your neural network will be wrong. Foxes are not dogs. So when there's an error, we need to look back at the weights to revise them so that the output generated by the neural network is correct. And to do that, we're going to look at the weights associated with any given output node and figure out what fraction of the error it's responsible for. So we do this for each weighted link that's associated with an output node. And we calculate these fractions for the errors for each output node. Okay. So once we know the fraction of the error each weight represents, we can use that to find the value of the hidden error in the previous hidden layer. The hidden error created 3 outputs in this neural network. And we can get our hidden error by multiplying each of these fractions by their error and adding them together. The same goes for each set of weights that come from a hidden error. And this is also represented by a matrix, so taking the transpose of the weights by the output error vector. Once you have the values of the hidden errors in the hidden layer, this step can be repeated to find the hidden errors of the previous hidden layer. So a neural network's error is a function of these internal link weights. Improving a neural network means reducing this error by changing those weights. So choosing the right weights directly to fix an error is too difficult, and an alternative approach is to iteratively improve the weights by descending the error function, taking small steps. We can use gradient descent to go downward from our current position, and we're updating the weights by changing them in the direction opposite to the gradient since we're looking to minimize the error. Each step is taken in the direction of the greatest downward slope from our current position. So an error function we might use is this one here, the square of the desired target minus the actual output, since this function would allow us to take smaller and smaller steps as the slope of the function nears 0. And this expression can be applied to all of the weights between hidden and output. Hidden and hidden, and the input and hidden. The learning rate in this function, the LR in this function stands for the learning rate, which will moderate the strength of the changes to the weights to make sure we don't overshoot our desired target. Otherwise, we may take steps that are too large and never end up at the minima. We just skip the fox here. And a problem we're likely to encounter, aside from that, or in general, is where our function might have a settle in a local minima other than a global minima. The best way to avoid this is to run a lot of test cases with different weights, different sets of weights, so that in some cases you don't end up with the wrong outcome. And that's all I have. David?
Yep, okay. Just to make sure, can you hear me all right?
I can hear you, yeah.
All right, let me share my slides. Can you see my slides?
Yeah.
Okay. So for the second half of this recitation, we'll be covering some of the more implementation side of neural networks and specifically feed-forward networks. So summary is we'll talk about tensors. Oh, and the package we'll be predominantly using in this course is PyTorch. So as part of this course, you'll have to learn it and work with it. So we'll cover tensors, CPU and GPU operations, and then the various components of training a model. Okay, so PyTorch's tensors are very similar to NumPy's ND arrays, if you have any familiarity with working with NumPy before. And I've listed a couple of similar points here. So you import them, of course, and then you can initialize both the, I should probably share this like this, okay. You can initialize both tensor and array by passing in a list or some kind of array-like structure. And you can convert between them very easily. So Torch has a lot of built-in functions that allow you to convert from a Torch tensor to a NumPy array. And then you can convert a NumPy array to a Torch tensor by just passing in the NumPy array to the torch.tensor argument. And a lot of the operations are the same. So PyTorch's tensor operations somewhat are based off of NumPy's tensor operation, NumPy's array operation. So at the bottom, you see that we initialized two tensors. Torch.randn generates a random tensor between 0 and 1, I believe. And then we set them to double because default torch tensors use float, but NumPy's use double, which has double the number of bits. And then we sent them to NumPy arrays, and then we compare the outputs of the matrix multiplication on those two tensors on both torch and NumPy respectively. And we see that the values are equal. Okay. Now, the main difference with PyTorch's tensor and NumPy's ND arrays is that you can perform operations on the GPU as opposed to the CPU. And performing matrix operations on the GPU is often much faster than working on the CPU. So I put an example on the left here, or on the bottom here. So I first initialized two 10,000 by 10,000 tensors, and I tried multiplying those two tensors on the CPU. And the time taken on the CPU is 21 seconds. So, and then to try it on the GPU, what you have to do with the tensor is first move it to GPU memory and then multiply them. So I display this to show a little bit of oddity with Torch as well. So the first time you move a tensor to the GPU, it's going to take a certain amount of time. Here you can see it takes 9 seconds, but the actual time taken to multiply on the GPU is only 0.01 seconds, as opposed to 21 seconds it took on the CPU. So the total GPU time taken is 9.97 seconds, but as you can see on the right, after you can kind of think of it like warming up the GPU. After you've moved something to the GPU before, if you try to move something else to the GPU, it's very fast. So time taken to move tensors to the GPU is 0.18 seconds, and then time taken to multiply in GPU is essentially 0. So you can see that there is a huge speed up from 21 seconds to 0.18 seconds, performing CPU versus GPU operations. So when possible, you should try to perform complicated operations on the GPU. So as briefly mentioned, to do GPU tensor operations, you first have to move the tensor from the CPU to the GPU. And there are a couple of ways to do this. So you first initialize the tensor, A, and then you can move it by doing A.2CUDA. And if you have multiple GPUs, you would do CUDA and then colon and then the index of the GPU you want to move it to. And you can also move it to a single GPU. By default, the first GPU is 0 by doing A.CUDA parens. And I don't know if I covered this, but one thing to note that is for tensors, if you want to move it to CUDA, you would have to do A.CUDA, and then that itself will return the new GPU-based tensor. But for more complicated structures like NN.module objects, you don't need to, it's in place. You don't need to reset the initial variable. And operations require all components to be on the same device, CPU or GPU. Operations between CPU and GPU tensors will fail. Okay, let me just double check chat just to see if there are any questions. Actually, it doesn't look like I can check chat in this mode. Oh, I can. Can you initialize the tensor directly within the GPU memory to avoid the moving time? So torch.tensor actually has an argument called, yes, a lot of functions in PyTorch has a device setting. So you can set device equals CUDA when you initialize it, but I think internally it's actually initializing the CPU and moving to GPU. So, and it looks like Jacob, another T, is looking at the chat as well. So I'll just proceed with the presentation. And Jacob can just interrupt me, or Mia can interrupt me if there's an issue. Oh, Rashmi's here too, nice. Okay. So here's an example of failure. First, we initialized two tensors A and B, and then we moved A to CUDA. So A GPU is on CUDA, and when you print out A GPU and B, you see a little device equals CUDA:0 on the right. And then I did C equals A GPU at B, which means tensor multiply A GPU and B to get C. But when I actually try to look at the value of C, it gives some kind of crazy error. And that's happening because A GPU was on the GPU, but B was on the CPU. And I actually put this on because this is on, well, I put this specific example up because this is on Google Colab. And this isn't actually error you would expect to get if you multiply a GPU tensor with the CPU tensor. Ideally, you would get the error when you actually multiply the two tensors. But as you can see here, yeah, I only got the error when you try to read out what C was. And you'll see this later, but this is one of the little things that's weird about Colab, I think. And yeah, so just be cognizant of where your tensors are when you do operations between them. Okay, things to keep in mind. A GPU operations runtime comes in two parts. So first, you have to move the tensor to a GPU, and two, the time taken for the operations. So number two is very fast on GPU, as you saw before. The actual tensor multiplication took only 0.01 seconds. But for sometimes, for small operations, number one can actually take much longer. And you can see that since we only use the tensors once for just one multiplication, moving took 18 times longer than actually doing the operation itself. So there's a trade-off here, right? So when you do operations, you kind of want to keep in mind, if you're adding or multiplying only like very small vectors, maybe like length like 3 to 5. This isn't like an actual number that you should memorize, but like just as long as you're aware that sometimes moving to the GPU can take much more than actually performing the operation. Sometimes it might actually be faster to just do that computation on the CPU. Second, GPU memory is quite limited, so you will frequently run into the following error. Runtime error, queued out of memory, yada, yada, yada. This basically means you try to allocate too many things to the GPU, and what you should look into is you should try to reduce the batch size or check if there are any dangling unused tensors left on the GPU. And if there are tensors left on a GPU that you don't want to use, you can explicitly delete those tensors by doing del A. If A is the tensor you want to delete, del A is just the Python command to remove the pointer to a object. And the torch q.empty cache, which empties any objects on the GPU that don't have any pointers to it, which means in more layman's terms, it just removes any unused garbage on the GPU, which should free up some memory. And you'll be encountering, this is probably one of the most common errors you'll be encountering this semester, so just work around it. Sometimes you'll have to iteratively print everything on the GPU to try to track down what's actually leaking. And one thing to note is, we'll get into the idea of a training loop later, but one thing that's nice to do is print out how much memory the GPU is using at every training iteration. Ideally, it should stay the same. But if it's increasing at every iteration, it means you have some loose tensors that you need to take care of. Now, this wasn't on the summary slide, but I thought it'd be important to do a couple slides on debugging, because although what you're learning from this course is DL, what you'll actually be spending most of your time doing is debugging. So it won't be working with data necessarily, it won't be developing new models. If you're unlucky, it might not even be training time that's longest. The time that you're going to be spent doing most is debugging. So it's actually important to talk about it. Okay, so this is what you should do when your code breaks. First, look at the error message. Expand the list of commands, the trace that led to the error. Then go to each of those lines in your code and see if you can find the problem. A lot of the trace will not actually be your own code. There'll be packages that you reference and use. You should read the documentation to see if you're using those correctly. Second, if you cannot fix the issue, you should Google your problem. You should read through all of the forums, Stack Overflow, PyTorch, GitHub issues, and a lot more, and try the suggestions that people have said fix their own issue. If you have no clue what these people are saying, you should go study the documentation, whatever package you're using. And because that's how those people learned what they know. And a lot of people think this is a waste of time, but I assure you that it's not, because this is how you learn to work with new packages / large code bases. One of the best ways to learn a new package, code base, yada, 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 is to keep bumping into walls and then try to get through those barriers by learning the nitty-gritty details behind the packages. And normally, outside of a class setting, the step 3 would not exist. So if you're doing research by yourself, or you're working on a project, or working at a company, you repeat step 2 or submit your own GitHub issue until your problem is resolved. However, since this is a class setting, you can go on Piazza or go to office hours at this step. But only do this if you have actually tried a lot of number 2. Generally, there are a lot of common issues that TAs will recognize, like what I said before, which was you run out of GPU memory. And if we see a post about you run out of GPU memory, or you try to do a multiplication between a long tensor and a float tensor, we will recognize these errors because we have run into these errors countless times in the past, and we have gone online and looked for solutions to these errors and fixed them. So we will know that these errors are generally things that are easily fixable if you take the time to go back and go through your code. In these cases, we will tell you to go look up solutions because A, we don't want a million of these issues that are bottlenecking us from solving actual problems. And B, we want you to develop skills that involve debugging, since not only in this course, but if you continue with DL, or I suppose programming in general, you'll be debugging for most of your day. And that's an important skill to learn. Now that we got that out of the way, the next couple slides include a couple of tips and tricks and common errors that you might encounter. And you might want to come back to these slides in the future if you have problems related to these. So you'll be running into CUDA errors like runtime error, CUDA error, device side assert triggered. And this is annoying because it's probably the most uninformative error statement you can possibly think of, besides probably segfault. This can mean many things. For example, you did an operation between CPU and GPU tensors, or you did GPU operations between tensors of unexpected shape. And this is likely the most common cause, at least in my personal experience. And another issue is your types were wrong in some weird ways. So if you're using some kind of cross-entropy class or function, it expects its inputs in a certain type, but if you put in the wrong type, sometimes you'll get this error if you do it on CUDA. However, the line the traceback shows may not actually be the source of error. And that's because in GPU operations, everything is parallelized to speed things up, and debugging is hard when stuff is run in parallel. And what you should try running is, after setting this environment variable, CUDA launch blocking equals 1, you should try running the whole thing again. And hopefully this time, the actual error message will be useful because this forces CUDA to do things sequentially, which is more likely to give you a better traceback. And remember to turn this back to CUDA launch blocking equals 0 afterwards. Otherwise, your GPU operations will be slow, like significantly slower, because if you have this environment variable set, CUDA doesn't really do much parallelization. Okay, so Colab, right? So these are some notes on working with Google Colab. If you aren't familiar with Google Colab, I think it's mentioned in Recitation 0 somewhere, but it's basically a Jupyter notebook that Google provides with the hardware accelerator, like NVIDIA GPU, that you can run a bunch of things on, and it cuts you off after 12 hours if you're on the free version. So Colab is great because it's free. But the problem is you'll run into some issues that give you a headache, besides it being all in one huge page that you have to scroll through. In a prior slide, note that the operation between the CPU and GPU tensors did not throw an error when you first performed it, but afterwards on another command. And this isn't actually expected behavior. Ideally, you would see the error thrown when you multiply the two tensors initially. And that's what you would expect to get when you work with AWS instant or locally. But yeah, that's one of the little things that Colab's going to be annoying about. So it's going to make debugging harder. When you get a device-side insert, you probably have to restart the entire runtime instance, because when you get a GPU-side error, things just stop working in general. If your NVIDIA MSMI, which tells you how much GPU memory you're using, shows clocked GPU memory, you have to restart the runtime instance. Among other issues, just take note, Colab is free, but you're trading your own time for it. Just evaluate your priorities and see what you want to do. Because in the end, the choice is up to you. Okay, so now we get into the components of training an actual model in PyTorch. So if I remember, the next 2 lectures will be on backpropagation, which is basically training your model, but you don't have any like in-depth exposure to that. So we'll just work with colloquial terms for now. So this is how you would, this is how you would describe training a model to someone who doesn't really know what backprop or loss function or and so on is. First, we get data, which are pairs of questions and answers. For a pair x, y, where x is the question and y is the answer, we run x through the model to get the model's answer y bar. Then an independent teacher gives the model a grade depending on how wrong the model's answer y bar is compared to the true answer y. And based on the grade, we figure out whose fault the error is. Then we fix the faults so the model can do better next time. So this is a 5-line, very simple way to think about what training a model is. And this is the general definition we'll work on for the remaining slides, and we'll expand on this as we go forward. So when training a model, data is generally a very long list of XY pairs where you want the model to see X and predict Y. And PyTorch has 2 classes that you will need to deal with this data: dataset and data loader. Dataset class is used to pre-process data and load single pairs XY, and data loader class uses your dataset class to get single pairs and group them into batches. So I forget if you've gone over the importance of a batch, but to briefly mention it here, batches, so, as I mentioned before, sometimes loading data into the GPU is actually, let's see, how do I explain this? In a lot of cases, batching your data and running the data through your model together. So running multiple pairs through your model together is a lot faster than running them one by one. So that's one reason we might want batches. And actually, I guess it's probably the biggest reason you would want to use batches. So generally, when you choose the batch size, you would put in as many as possible until your GPU runs out of memory. And yeah, so it's common to batch your data and run them through your model together. And at the bottom, a little diagram here. So if you zoom in the little data block, you get a data loader and the data set inside it. And I guess the most important thing to take into account here is the data loader takes in the data set as an argument. So the data loader makes batches out of the data set class you define. And you should just keep that in mind. Okay, so actual code. When defining a data set, there are 3 class methods that you need to implement: init, len, and getItem. So Torch will be using your dataset class internally to do some stuff. And the only 3 things that it's going to use are those 3 functions. So you just need to make sure those 3 functions are set. And it doesn't matter if you have a lot more functions or methods rather besides that. So you use init to load in the data to the class or pre-process it so it can be accessed later. PyTorch will use the length function to know how many XY pairs are in your data set. And finally, after using length function to figure out how many samples there are, PyTorch will use getItem to ask for a certain sample. So you can see here that getItem takes in index argument. So getItem I should return the ith sample with the order chosen by you. However, the order between different calls should be fixed. So if I ask for the ith index, and then a few days later I ask for the ith index again, then what you should return should be the same. Ask for the specific indices that PyTorch asks for, those would be randomized internally. So you don't have to worry about that in your dataset function. You should use getItem to do some final processing on the data before it's sent out. And one thing to note, getItem will be called maybe millions of times during your training loop. So make sure you do as little work in here as possible for fast code. So try to keep all the heavy processing in init, which is only called once. Also, generally, you don't have to worry about moving stuff to the GPU yet, because you'll do that manually in the trainer. But I guess for specific use cases, you might want to do that. But people who are familiar with those use cases will know to do that anyway. Okay, so now for the data loader. So here we define the data set that you defined before. You actually make an object instance out of it. Now, these are the arguments that you're going to be passing into your training data loader. So as you can see, it's a dictionary that we're going to expand out into quarks later. If you don't know what args or quarks is, that's a little thing that Python has, and you should look that up because it'll make your life a lot easier. Shuffle. We'll be going through the entire data set multiple times. We want to shuffle the data set every single time we loop through our training data loader. And that's been empirically proven to improve training performance significantly. So for training, you want to have this shuffle argument set to true. For validation or test, however, you don't want to shuffle because that might mess up the ordering in which you submit to the test server and so on. Batch size we talked about before. This is a hyperparameter you want to adjust. Batches are loaded in parallel, so this num workers controls how many workers you want to have that does this. So generally, 0 is actually I forget if 0 is well. Okay, for sure, 1 is just using 1 worker, so everything's loaded sequentially, and that's also what you want to use if you want to debug something in your data loader. 2, 3, 4, as you increase, generally you see an increase in efficiency. And then at some point, if you have too many workers, your efficiency actually decreases. So I generally seen for image-based tasks, num workers 4 works okay, but you should try a couple different numbers and see what gives you the fastest results. Okay, pin memory, it's just a little something that makes data loading faster at the expense of more RAM usage. As for specifics, we won't get into it. And lastly, we instantiate the data loader with our training loader args, as well as our training dataset that we initialized above. So yeah, notice that we give our dataset to the data loader so we can use it. Let me double check if there are any questions right now. Let's see. Oh, Tony's here as well. Yes, Windows does have an issue with num workers. And I believe in some of the starter code, we have a little if statement that says, use this if you're Windows, otherwise use this. Tony has it. So I'll just continue presenting. Okay, now we have our data set up. Next, we need to worry about the model we're going to use. And this entire section, at least for the model part, will be in 2 parts. So how to generate the model you use, and secondly, how to run the data sample through the model. In class, you went over the multi-layer perceptron, MLP. A bunch of these single perceptrons put together are called linear layers, also called fully connected layers, also called dense layers. Note, a linear layer is actually the connections between the 2 layers as shown on the right, so the actual red box itself. The layers themselves, so the filled in red box, the filled in blue box, green box, are actually the inputs themselves when they are run through the linear layers. So when we talk about a linear layer, we talk about the weights connecting to these boxes instead of the output or the input. A little subtlety, but that should help you realize that in the figure shown on the right, there are actually 3 linear layers instead of 4 layers. A key thing in neural networks is modularity. So the network on the right can be broken down into 3 essentially same components. So the 3 linear layers are in essence the same. The only thing that's different are the number of input/output features. When coding a network, you break down the structure into small parts and take it step by step. And this is beyond just modularity, object-oriented programming. This is a fundamental trend in ML as of now, using the same structure stacked on top of each other with varying feature numbers. So in CNNs, VGG introduced the idea of using the same, I guess this section's a little for people who have heard of these terms before, but VGG, one of the more original image CNNs, stacks the same layers on top of each other, just varying feature size. Transformers stacks 6 of the same type of layer in both the encoder and the decoder and so on. So just the idea you have to keep in mind is modularity. Let me get some water first. Okay, now let's get into coding a model in PyTorch. So networks in PyTorch are generally classes that are based off the nn.module class. So similar to the dataset class, PyTorch wants you to implement the init and forward methods. So these are the only two methods that PyTorch would expect you to implement. Init, this is where you define the actual model itself, along with other stuff you might need. Forward, given an input x, you run it through the model defined in init, and we'll see a more concrete example. So nn.linear class represents a linear layer, and nn.linear actually is a model class itself. It extends the nn module class and has a forward method. We'll be using this smaller model inside our own model, and this is a clear example of modularity. So on the right here, I have a screenshot from the documentation online. And you can see that nn.linear takes in features and out features as arguments. So nn.linear takes as input. So previously we talked about the argument to initialize it, and then the object itself takes in input some tensor of shape n asterisk in features. So n is the number of batches, star is whatever dimensions, and in features the actual number of features that you promise that you'll pass a linear function in the arguments. And then an output n asterisk out features. You can think of nn.linear transforming the last dimension. Now let's define our actual model. So the three layers defined in init correspond to the three layers on the right. So self.layer 1 is a linear layer from 3 features to 4. Layer 2 is 4 to 4, and then the final one is 4 to 1. And then in the forward function, we actually see that you take the input x, you run it through layer 1 to get output, then you run that output to layer 2 to get another output, and then you run that output through layer 3 to get the final output, and then you return output. So effectively, you're running x sequentially through each of the layers. And remember that nn.linear has trainable parameters, weights, and bias. And one thing you can try on your own as well is by calling dot parameters on our model, you'll see the weight and bias of each layer, thanks to some magic backend. And dot parameters tells you all the parameters in the network. You can also print out the model to see all the components, and you can see that this shows the 3 linear layers that a model is using. And one thing to caution here is that the code that works with this only looks at the stuff defined in the init and doesn't take into account what's actually used in the forward. So you can have a couple layers in the init that you're not actually using the forward, and you'll still print that here. So just something to keep in mind. And if you notice when I was saying, it gets a little annoying to type each of the layers twice, once in the init and once in the forward. Since on the right, we take the output of each layer and directly put it into the next, we can use the nn.sequential module. So the nn.sequential module takes a list of, well, it takes as arguments a bunch of modules. And then what it will do is it takes the input and runs it through each of the layers sequentially, runs it through each of the modules sequentially. So directly take the output of the previous module and put it into the next, one by one. You can do this in this case because we literally did that in our forward function. But if you want to do some process before, you can't use the sequential. But it does make the code a little simpler, since the forward is just running it through the layers, the sequential object. Since nn.sequential is an nn.module class anyway, we can make this even simpler. So we just directly initialize our model, instantiated our model to be an nn.sequential object here. And you can see we went from like 10 lines to 1, so it does make things a lot simpler. So far, we only covered the nn.linear class, and there are many more classes in PyTorch. Maybe like 30 or 40 more just to find an official package. Probably closer to 100. So as a beginner to PyTorch, you should definitely have the nn documentation open. The documentation is really, really thorough, and it even has a lot of source code. So I highly recommend you reference this as you go through this course. Also for optimizers, there's a separate documentation page as well. You should keep going through these pages until you're familiar with generally most of the things implemented here. All right, now that we have our model generated for the second part, how do we actually use it? So first we want to put the model on the GPU, and note that for the nn.module class, two devices in place. For tensors, you must do x equals x dot to device because it's not in place. That's just a little subtlety to note. I believe model to device actually does return the GPU model. So if you want to do model equals model to device, I think that's fine, but you don't need to. Okay, also models have .train and .eval methods. Before training, you should run model.train to tell the model to save gradients. And this is actually the default state of the model, but I just do it anyway, just to make sure there aren't any issues. Just to make sure there aren't any issues. So when validating or testing, you run model.eval to tell the model it does not need to save gradients. And this saves memory and time. It'll be significantly faster if you do this. And a common mistake is to forget to toggle back to train when your model doesn't learn anything. A common mistake is to forget to toggle back to .train when you actually train the model. Then since your model isn't saving gradients or whatnot, then your model doesn't learn anything. So I know we didn't really talk about what validating and testing is specifically, but for now you can think of it like the following. So when you train your model to do better on the test data set. However, you don't totally know how your model is going to do on a data set that it hasn't seen. So this is where validation or testing comes in. So validation, you run it on a separately split portion of the data set, and then you run things much like you do in training, and then you can get a loss function or a loss to see how your model is doing on a data set it hasn't seen. So that's just to test generalization. And for testing, you work on a test data set and you can submit that to the test server or whatnot. And as for the subtleties of optimizing for the training data set, validation set, I think you'll talk more about this in lecture. Okay, so I put together a little snippet of the most basic training code you'll see. So here's where we are so far. All the setting is done up there. So we initialize the data set, the model, put it to the GPU, yada, yada. Epochs are the number of times we run through the entire data set. So normally we'll train for multiple epochs, so we'll make multiple passes through the entire data set. Let's see. Within each epoch, we run through a train loader, which gives us X, Y batched. So train loader is, I think an iterator, no, it's a generator. So as you for loop through it, it'll give you X, Y pairs sequentially. And since the model is on the GPU, remember to put the X, Y on the GPU as well, or things will break. Afterwards, run X to the model to get the output. And we'll cover, the not yet covered portions we'll cover now. Okay, loss function. To recap, we have run X through our model and gotten output, or Y bar. And if you remember, we need something to tell us how wrong it is compared to the true answer Y. To do this, we'd rely on an X function, also called a criterion, to tell us this. The choice of a criterion will depend on the model / application / task, but for the classifications, the most common one is called cross-entropy loss. And you'll go through the specifics next lecture. Now, one thing I want to mention here is, this goes into specifics, but it's something you're going to run into when you start doing homework 1 part 2. Cross-entropy loss combines softmax and NLL loss. So you don't want to put in to cross-entropy loss your outputs after you run through softmax. What does that mean? After your final linear layer, you want to put in directly those outputs into cross-entropy loss. You don't want to run softmax before. And if you do that, that's going to cause your network to not learn. And I'm insisting on this because at least when I did this, I spent a couple of days trying to figure out an error, and that ended up being it. So that's a little thing that you need to keep in mind. Okay, so here we initialize the criterion, cross-entropy loss. And then we give our output and Y to the criterion. And this is the teacher we were talking about before. And it tells us how wrong the model was through a number called the loss. And through this training process, we want to minimize the loss. Now, backpropagation. Backprop is the process of working backwards from the loss and calculating the gradients of every single trainable parameter with respect to the loss. And the gradients tell us the direction in which to move to minimize the loss. And if this is new for you, don't worry. The next few lectures will make this very clear. But for now, we'll stick with intuitive explanation. Backpropagation is a method of assigning blame to all the little parameters in your network. And if you think about a single random parameter p in the model, backprop will give us a number for p. That's not delta, but delta p. Delta p tells us, hey, p is not optimal, and it caused the final out to be different from true answer. And this is how much p was wrong, and we should change p by delta p to make the final output much better. And this is what backprop tells us. So we should look at the number assigned to every p and use it to fix p to do better next time. So this is what this does. So loss.backwards computes all of those, I guess it's nabla, I think, nabla p's, and we get the gradient with respect to a loss. And remember model.train, that's what allowed us to compute the gradients. If it had been in the eval state, we wouldn't even be able to compute the gradients, much less train. And this semester, you'll work with a lot of the background stuff, the back-end stuff, regarding backpropagation, loss function, gradients in your homework 1 part 1. So you'll get very, very familiar with all these concepts. Optimizer. Now backprop only computes the nabla p values. It doesn't actually do anything with them. Now we want to update the value of p using nabla p, and this is the optimizer's job. A crucial component of any optimizer is the learning rate. This is a hyperparameter that controls how much we should believe in nabla p. Again, this will be covered in more detail in future lectures, but ideally, what you should understand here is the intuitive understanding behind it. Ideally, nabla p is a perfect assignment of blame with respect to the entire data set. In other words, nabla p is exactly what we want to do to get p to the optimal value. However, it's likely that optimizing to perfectly match the current XY sample nabla p was generated from won't be great for matching the entire data set. What does that mean? That means if you look closely, we generated nabla p when we did loss backward, right? But loss backward is only done on the current XY sample that we're looking at. And that doesn't tell us much about the entire data set. So if we make our model really good at this specific X and Y, it might get 100% classification accuracy or whatever on this specific XY, but then you're going to move on to the next sample and realize that our model didn't really learn anything for the next sample. So the learning rate is based on how much you want to trust this current sample. And among other concerns, the optimizer weights the nabla p with the learning rate and use the weighted nabla p to update p. Now here we initialize the optimizer with learning rate 1e-4, and Atom is just likely one of the 2 optimizers that you're going to be using a lot in this course, along with SGD. And you can note that we gave model.parameters to Atom. So it's going to look through all the trainable parameters in the model, and when you do loss step backwards again, it's going to compute. That's not true actually. It's going to update all of the trainable parameters when you do optimizer.step. Optimizer.zeroGrad. What is zeroGrad? Every call to backwards saves the gradients for each parameter in the model. However, calling optimizer.step does not delete these gradients after using them. So you want to remove them so that they don't interfere with gradients of the next sample. And that's what zeroGrad does. And by doing optimizer.step, we update the weights of the model using the computed gradients, computed in loss.backwards. Important. The general order of these steps are crucial. We run X through the model, we compute the loss, we run loss.backwards to compute the gradients, then we step the optimizer, and then in this loop or the next, we zero out the gradients. And this is something you should keep in mind. At least I found it really useful just to keep this general structure in mind when you make your own pipeline or when you read other people's code. Because generally, no matter how complicated data, how complicated the model is, these steps are something that any code base follows. So as long as you identify these 5 steps, you can work backwards to decompose more complicated code bases. some extras. So after here, after every epoch, you would generally perform validation to see how your model performs on data it's not trained on. And validation follows a similar format as training, but without lost step backwards or optimizer that step. And we have a couple of Jupyter notebooks that you can follow for guidance. So I think we actually have some time. So I'll take questions here. If something confused you during the lecture, you can ask now and I'll try to answer.
Hi, can you just explain the zeroing of the gradients that we do after after the optimizer step?
Sure. So the optimizer. So let's look at these individual steps. Loss stop backwards computes each of the gradients with respect to a loss. So what it does, if you actually go in and print the parameters, you'll see what did I just do? Okay, you'll see the parameter and the gradient attached to it. Now suppose this is nice because you can just use the gradients to adjust the parameters using optimizers.step. But the problem is if you do a loss step backwards again on the next sample, you'll add to the gradients here. So optimizer.step doesn't delete the gradients after using them. It keeps them as is. So in the next sample, you'll do loss step backwards and then it'll add to these gradients and so on and so on. But that's not what you want because you already used the gradients in the last loop. So what you want to do is zero out the gradients to have a clean slate for the next iteration of the train loader to put the gradients in. That got a little convoluted, but did that make sense to you?
Yeah, it's fine.
Okay. Is there I see other TAs, well, a lot of TAs answering questions as well, but I'll just post them off too. Is there any case where we don't want to zero gradients? Let's see. Yes, yes. In this case, in a lot of cases where you have only loss function, I think for almost every single thing here, thing in this class, yes, but when you have a more complicated structure, more specifically multitask loss. So when you're optimizing for multiple loss at the same time, you'll do loss stop backwards on loss 1. And then since you also want to optimize for loss 2, you'll do loss 2 stop backwards on there too. So you'd accumulate the gradients from 2 different sources. And then you would do optimizer.step. And afterwards you would do, and then you'll zero out the gradients. But actually, I guess you zero out the gradients anyway. I think PyTorch just separates the optimizers.step and optimizer.zeroGrad just to give more freedom. It doesn't want to lock you into having to zero out the gradients every single time. But yeah, I'm sure there's a use case in which you don't want to zero out the gradients. I saw someone raise their hand.
Yeah, that was me.
Okay, yeah.
Could you accumulate gradients between iterations to effectively train on larger batch sizes without having to do it all at once?
Oh, I see. Can you accumulate gradients? Yeah, I mean, okay. Simple answer, yes, you totally can. Let me try to think of why that's not commonly done. Actually, yeah, really, that's right. That would be batch SGD. Actually, what you're doing every iteration is batch SGD anyway, because you're running on batches at a time. I guess my answer for that would be that's not fundamentally very different from just changing the batch size. And understandably, if your data is too big or your model is too big and you run out of GPU, this is one way. That would be one way to artificially increase the batch size. But doing this isn't necessarily helpful because what batch does is it also decreases the variance. How do I explain this? Did you guys cover like variance and variance of batches? Like single sample SGD, batch SGD, and entire data set SGD, did you guys cover that in lecture yet? Oh, no, okay. So basically, just to give a little teaser, I guess, is for a single sample, just like drawing from any distribution, a single sample has a lot of variance. And what batch does is, if you batch it, if you draw 5 samples and take the average of those, you wouldn't actually take the average of those, but when you take 5 samples and take the average, you decrease the variance effectively. And the least variance would be if you did this on the entire data set at a time.
Right.
So batch serves that purpose as well. And yes, you could totally do this. I guess you could do it if you don't have enough GPU memory, but it would slow down your trading as well, because you're only stepping, if you did this every 2 batches, you're only stepping half the time.
Right. So I guess the reasoning that it's not super common then is that it kind of defeats the purpose of the batches?
That's not necessarily, I would hesitate to say that, but I think if I were to give you a straight answer as to why it's not commonly used, is it's not commonly used because there's no real reason to do so, because you can increase the batch size, and if you're empirically, I guess, you don't need to do this. I mean,
Okay.
you're going to run into this a lot. People are going to have great ideas, and a lot of the justification will be, we ran it a bunch of times, and then it ends up being better. So yeah,
Okay.
sorry if that's unsatisfying, but yeah.
That's all right. Thank you.
Someone raised their hand. Matthias, you can answer.
Yeah.
You can ask. Yep.
I had a question about the for loop on the training, the for epoch and the model.train.
Okay.
So my question was, so you're doing this 100 times, and
Yes.
every iteration you're calling model.train. From what I understand, every time you do an epoch is keeping what you trained on and keeping training again, right? Like cumulative training.
Yes.
And is model.train like resetting anything there, or?
No, model.train doesn't reset anything. So every nn.module class has a little attribute, I think it's called is_train or something like that. And that just tells the model whether to accumulate gradients or not. So model.train toggles is_train true recursively. Eval toggles it false. That's all it's doing. It doesn't delete anything.
Thank you.
Nice. Okay. Shriti, I see you raised your hand.
Yeah. I have one same question on ZeroGrad, optimizer.ZeroGrad. So
Okay.
I just saw one Stack Overflow post in which it said that in models like RNN, we don't explicitly do optimizer.ZeroGrad, but it's only for like simpler models. Can you just explain that?
You don't do optimizer.ZeroGrad for RNNs. Is that true? It's hard to answer this with more context, because at least when I worked with RNNs in this course, I definitely did ZeroGrad.
Okay.
So I'm not totally sure. Maybe if you find the Stack Overflow post and you make a post on Piazza, we can look into it. But as for right now, I'm not totally sure what use case that would be.
So I'm just making sure it's a general practice to do optimizer.ZeroGrad
Yes.
in the training loop.
Yes, it's general practice.
Okay. Thank you.
Alex Quark, I see you.
Oh yeah. I see here like the number of epochs are 100. Is there like a common practice on like setting the number of epochs, or like to know like when to stop training? Like, can you give any advice?
Okay, so that's a hard question, because there's no good. Okay, well, the answer is that there's no good answer. I guess the best answer that I can give is you keep training until your validation loss, or whatever metric you're measuring, your validation loss keeps decreasing. So even if your validation loss decreases a tiny bit, you keep training until it stops decreasing. And as for what point that is, it depends on way too many factors. So it depends on, just to name a couple of things, it depends on your learning rate for sure. It depends on your criterion for sure. It depends on your optimizer, definitely. What we didn't cover here, that's also a huge part of training, is the scheduler. And the scheduler, loosely just to describe it, is empirically it found, well, I mean theoretically actually too, decreasing your learning rate, or not necessarily decreasing, but changing your learning rate over time has been shown to improve training a lot. And what the scheduler does is change up your learning rate over the epochs or over the samples. And it depends on a lot of these factors, whether like, yeah, it depends on all of these factors. So there's no concrete way to say, okay, for this application, train for 100 epochs, for this application 200. You just want to keep training until your validation loss stops decreasing. And then at that point, you just cut off the training, because afterwards, you're not doing any better.
Okay,
And
thanks.
I think we'll put up a little post about just training practices, or we'll see. Just keep an eye out for that.
Okay, thanks.
I forget who raised their hand first. We'll go with Daniel first, since I answered a question from Shruti before. Daniel Mo.
Yeah, hi. So yeah, I'm wondering, so if we're going to do some validation inside of each epoch, so I'm wondering if we need another data loader for validation dataset, or we can just add another parameter to data loader, so you know, it both like generate the training set and validation dataset.
Yes, you generally will have 3 data loaders: one for train, one for val, one for test.
Thank you.
And if you look at the notebook on this final slide, these have 3 notebooks. One with MNIST, the classic MNIST training example. I think you'll see an example of that.
Sure. Thank you.
Shruti, I guess, I mean, if your question got resolved, that's good. Any other questions? Okay. If there are no more questions, we can start wrapping up. I guess since I have an audience here, I want to just mention, since this is the recitation for teaching you how to write DL code. So one thing you're going to realize when you start doing DL stuff is that there are a million hyperparameters that you're going to have to set. So even on this page alone, I think there are like 10, or let's see, there's the model, there's the number of epochs, the criterion, the optimizer, the learning rate, the batch size, and I guess you can put transforms in there. So only in even on the most simple training loop, you already have 6 parameters, and that's just counting model as a general umbrella. And in the model itself, you're gonna have like a lot more hyperparameters. And when you run a bunch of DL experiments, what you're gonna realize is that you want the place to keep track of everything you've run so far. And this is very implementation based. It's not like something cool or shiny, like in the architecture or whatever, but you want to set up your environment or your infrastructure so that every time you run an experiment, you save everything related to that model. And when I say everything, I literally mean everything. So you want the log file or whatnot. Like what I have set up is it literally copies the entire code folder into another folder. So if I want to run that experiment again, I can just go to that code folder and just run that specific snapshot of the training. And you might currently underestimate the importance of this, but it gets really annoying later if you have a really good result, but you're like, hey, I want to replicate that, but you have no clue what actually led up to that result. And that gets really annoying later. So I strongly recommend you do that. Another thing is you should get that set up really quickly, because once you set up the infrastructure for homework 1, you can use it again for homework 2, 3, 4. So I strongly recommend that. AWS. I strongly suggest you look into spot instances. If you want to look into spot instances, you have to request access for spot instances separately from normal instances. So you should get on that if you want to look into those. Spot instances, people are a little scared of them because they're afraid their code will just disappear. And you can prevent that by, when you make the volume, you can do terminate with instance false. And that's just a little thing you can set when you make the volume. So even if the spot instance dies, you can actually you can keep the actual hard drive and attach it to your next volume. So that's a little trick that I strongly recommend. What else is there? Keep your code organized. When you come to office hours, it helps TAs a lot if you have your code organized into separate files, or if that's not possible, separate portions. And I think that's all the tips from me. If any of the TAs have any other tips, since we have a wide audience here, they can unmute and talk about it, but that's all it for me. Revneet, I have a question using package for the homework assignments. Where should I post that on Piazza? Homework FAQ thread, probably. Yeah, that's probably a good place. So yeah, if there are no other comments or questions, I think that's it for this recitation.
Sorry, can you repeat your first tip again?
Repeat what?
Sorry, can you repeat your first tip again?
What was my first tip? Does anyone remember what my first tip was? If you remember.
Is it volume 1?
What was it? Sorry.
Is it the volume with Amazon volume?
Okay. I can. If that was my first tip. The first tip was. Oh wait, it was saving my model. Okay, I'll go over saving my model first. Okay, so you're gonna have a lot of hyperparameters when you train the model related to the model itself and then the actual training. What I recommend is set up some code that will save everything related to your model in a separate log file every time you run the training loop. So I think I'll post some code about this since this isn't directly related to the model itself, but what you want to do is generate a new folder, copy everything related to train the model to it, and have a log file with all the hyperparameters listed. So when you want to run that specific model again, you can directly do it. Save the model and the weights. I should mention this. In your training loop, it's customary. It's a lot of people save their model weights at every epoch. So you can load the model weights directly in if you want to resume training. Yes, that's something you should do. Just keep in mind your models can be large, so just keep an eye on memory usage. And spot instances, I mean, I guess I'll just repeat it. Spot instances, 1/3 of the cost of regular instances. Drawback is that spot instances, they can die randomly, but you can kind of alleviate this issue by making the volume attached to it not disappear when the spot instances die. So you can just attach it to the new instance. Can you also post? Yep. Okay, I can make a post on that today or tomorrow. Yeah, so if there are no other questions, thanks for coming to the first recitation. I strongly recommend you get started early on these homeworks. And I know you've heard this in every class you've taken so far, but especially this class, because this isn't, like training a model isn't something you can do the day before, right? Because the training process itself takes multiple days. So strongly recommend you get started early. Can you make a good Piazza post on good practice and training? Yes, I'll make that. Okay, thanks for coming to the recitation. Good luck on your homeworks. I'll end the recording here.